Have you ever stopped to think about what's really going on inside that black box sitting on your desk? We use them every single day, but let's be honest, how they work can feel like total magic. Well, in this explainer, we're going to pull back the curtain and find out how they actually work, step by step.
Think about it. It's something we do hundreds, maybe thousands of times a day without a second thought. You press a key and boom, a letter appears on your screen. It feels instant, right? But underneath that simple action, there's a really fascinating and logical process going on. So let's explore that together. To really get how a computer works, we need to start with one super simple core idea. When you boil it all down, a computer has one main job: to be a processor for data. So what does that even mean, a data processor? Well, it's just a device that takes in all sorts of raw facts and figures, we call that data, and then it follows a set of instructions to turn all that raw stuff into something useful, something meaningful. And that we call information. This little diagram shows that perfectly. You've got data going in. That could be anything from you clicking your mouse to typing a letter. The computer then processes it, and what you get out on the other side is useful information, like a finished document or a picture you can see. Input, process, output. That's the fundamental loop of everything a computer does. Now, the part of the computer that handles all this processing work, that's the central processing unit, or the CPU for short. And honestly, the easiest way to think about the CPU is to just think of it as the brain of the whole operation. Okay, so if the CPU is the brain, what's actually going on inside of it? Let's take a look under the hood and see what this electronic brain really does. Think of this as kind of a computer's nervous system. You've got your input devices like your keyboard, your output devices like your monitor, and storage like your hard drive. But right there in the middle, connecting everything, is this CPU. It's the command center that directs all the traffic. But here's the thing. The CPU isn't just one big single part. To handle all of its jobs really efficiently, it's actually split into two specialized parts that work together perfectly as a team. So these two main parts are the control unit, or CU, and the arithmetic and logic unit, or ALU. Think of the control unit as the director or the traffic cop. Its job is to grab instructions and coordinate everything. Then you have the ALU. This is the calculator. It's the part that does all the heavy lifting with math and makes logical decisions. All right, so we have a director and a calculator. That makes sense, but how does a device made of silicon and wires actually think? How does it know what instructions it's supposed to follow? I mean, the CPU can't understand English or any other human language. It needs its instructions delivered in a language that it's built to process. So what language does this electronic brain speak? It speaks a language called binary, and it's actually incredibly simple because it's only made up of two symbols, 0 and 1. Since computers are electronic, this is a perfect system. You can just think of a 0 as an electrical switch that's turned off, and a 1 as that same switch being turned on. Now, just take a moment to really let that sink in. Every single thing you see and do on a computer, every photo, every song you listen to, every website you visit, it's all ultimately just a massive, incredibly complex pattern of these simple on and off states. Billions and billions of zeros and ones. So how do we get from the letters we type on a keyboard to the ones and zeros that a computer actually understands? Well, it all comes down to a translation step. Let's see how our world gets translated into binary. For a computer to understand us, everything we give it needs to be converted. To do this, computers use a standardized code. It's kind of like a translation dictionary that gives a unique number to every single letter, symbol, and character we use. A classic example of this is a code called ASCII. As you can see, the capital letter A is assigned its own specific binary pattern. B has its own unique pattern, C has another, and so on for every character. So when you press a key, the keyboard sends that specific binary code straight to the CPU. Okay, so now we have all the pieces, right? We have the brain, we have its special language, and we have the translation code. Let's put it all together now and follow the journey of one single command from start to finish. This whole process is called the instruction cycle, and it happens millions, sometimes billions of times every second. It's got 4 steps. First is fetch. The control unit grabs an instruction from the computer's memory. Second is decode. The control unit figures out what that instruction actually means. Third is execute. The instruction is sent over to the ALU, the calculator, to do the actual work. And finally, step 4 is write back.
The result of that calculation is stored back in memory, ready to be used. Fetch, decode, execute, write back, over and over and over again.
So, after going through the CPU, binary, and that whole instruction cycle, what's the one crucial point you should really take away from all of this?
It really comes down to this. A computer is a processor with a brain, the CPU, that follows a long list of instructions by speaking a very simple language of on and off switches called binary. That is the foundation of everything a computer can do. What's really wild is that everything else, from incredible video games to artificial intelligence, is all built on top of this simple on and off foundation. It really leaves you with a final thought, doesn't it? What else is built on this simple language? The answer is pretty much our entire modern world.